Welcome to Unit 3, Lecture 1, Section 2.2, talking about properties of water. The learning objectives are: explain the unique properties of water, explain how water's polarity affects the way water interacts with other substances, explain why buffers are important to the survival of an organism. So, the water molecule. Water molecules are what's known as polar. So the phrase polar basically means the same as you would with the poles on the planet. Okay, North Pole, South Pole. They're opposite ends of the planet. So what polar means is just two sides of the molecule. And what happens here is the water molecule charges are unevenly distributed. Water is technically neutral. It means there's technically no charge. But on one side of the molecule, there is a negative charge, okay? And on one side of the molecule, there's a positive charge. So oxygen has a slightly negative charge, and hydrogen has a slightly positive charge, because what happens is these little negatively charged particles called electrons, you probably remember that from earlier in your science classes, okay? Electrons have a negative charge. They actually spend a lot more time around the oxygen molecule. And what that means is that creates a slightly negative charge over here, okay, versus the slightly positive, so that, the slightly negative charge over here, versus the slightly positive charge over here. Okay, and what that means is that there are charges here, and just like magnets with different charges, that's exactly like what a water molecule is. So a magnet, you may remember from earlier on in science classes in middle school, elementary school, magnets have opposite sides, negative or positive, or sometimes called the North Pole or the South Pole. Okay, and what happens is opposites attract, so magnets that are opposite like to stick to each other. And so what this does is this makes water operate in a lot of the same ways. So you can see negative and positive. So what happens is these negatives and positives end up being attracted to each other in a hydrogen bond. So this hydrogen bond right here, okay, is a connection between that positive hydrogen and that negative part of another oxygen. And that hydrogen bond allows the water molecules, so we have different water molecules sticking together. So that hydrogen bond is allowing these different water molecules to hang out together. So that attraction between the two creates something called cohesion. So cohesion, whoops, I meant to put the highlighter on. Cohesion, okay, is the attraction between molecules of the same substance. So that attraction between the hydrogen of one water molecule, okay, that hydrogen bond attracted to the oxygen of another water molecule. Okay, and so that cohesion ends up causing water to stick to itself. Okay, it makes water sticky. It makes it act like Velcro. Adhesion is a little bit different, where we have adhesion is where we have the attraction of molecules of different substance. So in this case, we end up having adhesion. Whoops, change color. Okay, adhesion is where the water is actually kind of traveling up the glass. Okay, and you can kind of see it. And if you remember, from previous science classes, when you're reading a graduated cylinder, you have to read that meniscus. okay? Because what happens is the water is actually traveling up the glass, and that's actually adhesion. So that's the water is actually just sticking to the glass and kind of pulling itself up a little bit. Now, the funny thing about adhesion and cohesion is working together, they actually create a lot of all of the magic that water does in the natural world. So you can see as it travels up, okay, and depending on how thick the tube is, so you can see we have a real thin tube, it's real thin here, it's a little bit thicker here, and then it's a real wide diameter here, okay, that water can actually travel up different lengths, okay. So another one of water's magical properties is called heat capacity. Now, heat capacity is officially designed or defined, okay, as the amount of energy needed to raise a substance temperature by making its molecules move faster. Okay, so you remember that molecules can be arranged as a solid, a liquid, okay, or a gas. And heat capacity is the ability or the energy it takes to make a solid become a liquid and a liquid become a gas. Water has a really high heat capacity. So what that means is it can absorb a lot of energy, okay, before making that transition. And what that does is that allows substances that are water-based, okay, to resist temperature change, okay, to help with cooling processes and so many other things. So this is where sweat comes from, okay, sweat comes from the heat capacity. So what happens is your body, the water in your body is absorbing that energy, okay, to help keep you stable, okay, and then when it starts to get too much, it then pushes it out, causing sweat, which then also evaporates off your skin to cool you down. So that's a whole another side of things. Okay, all right. The last real, well, not the last, kind of, but the another property of water is that it's known as the universal solvent. Okay, it's the universal solvent because its polarity allows water to dissolve things that have other charges. So whether we're talking about an ionic compound, which is an ionic bond, like salt, where we've got an Na, so we actually have a plus and a minus, or a polar molecule that kind of has a plus and a minus. And so what happens is this universal solvent, so if you're making coffee, tea, hot chocolate, okay, any of those things, a powdered energy drink or whatever, all of those things, the polarity of the water is actually allowing that molecule to dissolve. So you can kind of see here, okay, all right, the water molecule, and you can see up here in this top one, you see it's the blue of the hydrogen, which you remember is positive, okay, is being attracted to the negative of that chlorine gas, or the chlorine gas, of that chlorine molecule. All right, and what it's doing is it's actually pulling it away from the rest of the salt, okay, and breaking it up. So that's how you can make salt water. Okay, and last but not least, we're going to do a little bit of refresher about the pH system, or the pH scale. We're going to work with this in class, but lower pH is acidic. All right, so down here, so the bottom part, so that's usually 0 to 7, and then high pH, oh good lord, high pH is 7 to 14 is basic. And there's a difference in ion concentration. So acidic have an increase in hydrogen ions. Okay, many more hydrogen ions. And then the high pH, okay, the basic solutions actually have a much lower condition of H plus ions. So pH is the amount of hydrogen ions in solution. Okay, and it talks about whether something is acidic or basic depends on how many H plus ions. Now, if you take H plus ions, okay, the other side of the H plus ions, okay, are OH negative ions. And if you put H plus and OH minus together, what do you get? You get water. Okay, so that's why neutral, which is 7, okay, that's why neutral right here is actually pure water. Okay, pure water is because we have an equal number of H plus ions and OH minus ions, and that actually ends up creating water. Okay. So we're going to look at the pH scale. So most of our functioning for our body is actually in the 7 range, usually 6.5 to 7.5. Most of our bodily pHs stand, except for our gastric juices, which we'll talk a little bit about. So stomach acid is way down here, usually in the 2 range, okay, because its job is to actually break down, what's it called? Is actually to break down food. So acid helps break down food, and we'll talk a little bit more about that, okay? All right. So buffers are a special kind of solution that actually help maintain homeostasis. Homeostasis, way back in Unit 1, talking about homeostasis. Homeostasis is just balance. It just means balance. So buffers actually help us maintain that balance. So what we do is we end up if we add acid, okay, to an unbuffered base, which is what we have here. So the red is more acidic, the blue is basic. So if we add acid to just a base, okay, all right, we're going to actually turn it, we're just going to turn it acidic. Whereas if we have a buffer in place and we add acid, we actually are going to minimize that pH change. So buffers help to minimize pH change, okay? They help to minimize pH change when conditions are not optimal, okay? So if for some reason your system is not in optimal condition, this helps to minimize that pH change, all right? Okay.